A square plate of copper with 55 centimeter sides has no net charge, and it's placed in a region of a uniform electric field, 75,000 newtons per coulomb, directed perpendicularly to the plate. We want to find the electric flux through the plate faces. First, I'll draw the plate. But a plate of solid copper has a significant width to it, so it's not an infinitely thin plane. The bottom width of it is going to be 0.55 meters, and then the height of it will also be 0.55 meters. And they didn't say what the thickness was going to be. The electric field vectors flowing through the plate's surfaces are going to come out perpendicular to the plate. These are the electric field vectors. Now, what will happen to a conductor when it's in the presence of an electric field like this? We know that many electrons in a conductor are free to move. So if they're in the presence of a field, they're going to feel forces that cause them to move toward a certain side of the object. Now, positive charges would move in the direction of the field, but negative charges move in the opposite direction. This means that the left side of this object is going to acquire a net negative charge. And since there'll be a deficit of electrons, that will make the right side of the object positively charged. So there's a separation of charge. Now we know the strength of the field is 75,000 newtons per coulomb. And we can also find the area of each face of the copper plate. It's going to be .55 meters squared. This is 0.3025 square meters. So the flux through a face will be easy to find now. It'll be the field strength times the area because the field is uniformly distributed. So the flux through the positive side of our copper object is going to be 22,700 Newton meters squared per coulomb. Interestingly, the flux through the back side will be the opposite. It's interesting to point out that the net flux here will be 0. But it's also interesting to consider that the rearrangement of charges inside the object itself creates its own electric field. So if we take a look at a cross-section of the copper, there's an external electric field which cuts right through the object. This causes charges inside the metal to rearrange so that we have positives on the right and negatives on the left. But the positives and negatives create their own induced internal electric field, which opposes the external electric field. So the green is the E induced, and the blue is the E external. By superposition, since we have one electric field pointing to the left and one pointing to the right, they will actually cancel out. The external magnitude of electric field is 75,000 newtons per coulomb. So the way that the charges rearrange inside is that makes an internal electric field of also 75,000 newtons per coulomb. The net result of this, though, is that the electric field inside is 0. And the electric field outside stays 75,000 newtons per coulomb. All right, now we want to find the total charge on each face of the copper plate. For that, we can use Gauss's law. In order to use it, though, what I'd like to do is split up my object into two distinct pieces. One piece will contain the positively charged face, and then the other half will contain the negatively charged face. Now imagine we create a giant cylinder where the cylinder contains 1/2 of our copper plate. Inside it, and we make another cylinder which will contain the other half. The cylinder on the right contains the positive plate. The cylinder on the left contains the negative plate. And now this is a good start, but we'd really like to shrink our cylinder down so that we can really capture what kind of field is leaving the plate. So I'm going to shrink it down to a box that is just slightly bigger than the plate itself. We know that the field near the plate's surface is going to come out perpendicular, and it'll be nice and uniform. And we just want to capture how much flux is leaving that front face. We'll multiply the external electric field times the area of the shape. We had calculated this earlier to be 22,700. That's the flux leaving through the front. But let's remember that we contained the front half of the copper plate in a Gaussian surface, and the back half is contained in its own Gaussian surface as well. How much flux flows through the center? The answer is 0. We know this because the electric field is 0 inside the object. So we have Gaussian surface A and Gaussian surface B. The total flux through A is due completely to the flux through the front surface. So that's going to be the 22,700. We want to set that equal to the charge enclosed by A over epsilon naught. So we'll multiply, and we see that the Q enclosed by A is 201 nanocoulombs. So there must be positive 201 nanocoulombs on the positive plate. And by the symmetry of the situation, there must be negative 201 nanocoulombs on the negative plate. So the beauty of these Gaussian surfaces here is that we will have no flux on the top, no flux on the side, and no flux between them either. there will be no flux through the middle. Only one face of the box will have flux, and that's the front. The last question asks us to find the surface charge density on each of the faces. So for that, I'll use the formula for surface charge density. Plug in my 201 nanocoulombs and my 0.55 meters squared. The surface charge density on the positive plate is going to be 6.64 times 10 to the minus 7 coulombs per meter squared. And then the surface charge on the negative plate will be the opposite. Previously, we had said that the electric field due to a plane would be given by the formula sigma over 2 epsilon naught. We also said that the electric field due to a capacitor would be sigma over epsilon naught. This piece of copper becomes like a capacitor, but it has material between its faces. Let's see what the induced electric field would be between the positive and negative sides of the copper plate, using the numbers that we had found below. If we divide, we get that the induced field should be 75,000 newtons per coulomb. Now the reason why we don't see that field inside our copper object is because there's an external field with an equal magnitude. The external field is 75,000 newtons per coulomb. So even though we have field going through to the right, we also have field going back to the left with an equal magnitude, canceling out in the middle.